Right, so let me get to this and share my screen. All right, let me do the slideshow. All right, so welcome to the January 28th internship now N3 monthly meeting. We're going to talk about the internship and we're going to hear from our colleague Bryan Méndez. Probably the next meeting will be February 18th or 25th. And I think at that one, we're going to ask one of our, one or two of our um, former mentors to present,
Well,
especially ones who are going to, go ahead.
the interns want to, some of the former interns want to
Oh,
present
the
as
interns.
well.
Yeah, yeah, yeah.
Right, not the
Um,
mentors. Yeah,
the
so
but we might want to do the ones with interns who presented with their mentors at conferences. Is that what we were thinking of?
those might be some of them as well. Anyway, well, there we have a number of volunteers. We'll have to see who's really available.
Yeah. All right. So this is mainly for you, this first part, Sarah, which is we're going to talk about the internship application, which is live and out and ready to be completed. And we're going to share that around. And then we're going to have Dr. Bryan Méndez from UC Berkeley. He's going to talk about the Carruthers Geocorona Observatory. And he's also part of our N3 team and has helped us make curriculum as well as done a lot of professional development for teachers. All right. So I can help talk about the applications, but Lynn, you should also weigh in on this as well. This is the application link. So, um,
Yes. That's
and you
the
can
link
also,
to the page that has a lot of important information on it, including the link to the actual application.
yeah,
So that page has information for the recommenders, it has information for your parents, it has information for the applicant. Everybody should read it and look at all the FAQ answers too.
yeah. And it actually gives you the questions that you can read through before you actually have to fill it out in the form.
Right, you can download a PDF of the actual questions so you can work out your answers before trying to fill out the form.
Yeah. All right. So here's some recommendations for filling out the application. Okay. Um, First of all, make sure you're eligible. Carefully read what it says online for the age and, that you need to identify as autistic and um, you want to make sure you've taken the right course, science and math courses and things like that. Make sure that you can do it. Okay. We've sometimes had people who wanted to do multiple internships over the summer, and this is a very challenging internship. It requires a lot of hours and it requires a lot of thinking and working with a mentor. So please make sure that you're not like going away for 2 months of the summer if you're going to do it and apply for it, okay? Um, and then look into the program. There's lots of information up there about other interns that have done it and other projects that have been done. So please look at those. And especially, it's really valuable if you tailor your application to what you see other people have done. It's really helpful for us when we're reviewing the applications to see like where you might fit in with other mentors um, who are looking for interns. All right. So being very specific about what topics you're interested in, what projects you might want to do, what skills you bring to the internship. All right. Then we have some essays, application essays. They're not super long. All right. So one thing to make your essay stand out, please avoid cliches. Even if you have always loved space and loved NASA, we see a lot of that when people apply. So, being really specific about what is it that you've really liked and what things are you interested in and research that you'd like to do. Um, that will really make your application stand out. All right. Are you a good coder? Are you someone who has really researched a certain topic a lot? Do you have experience out in the world that relates to it? Have you visited NASA centers? Have you always been interested in climate change or in black holes, things like that? Let us know about that. And what do you hope to gain from the experience? What do you hope you'd like to do with your life? Be a NASA scientist, be you know, a climate activist, anything like that. We really want to know who you are and what you want to do with this experience. And the start and ending paragraphs are the most important, right? That's what we like remember from when we review them. All right. We ask for letters of reference from somebody, one of your teachers, or somebody that will be able to really talk about you. So make sure to please, the applications are due March 1st. Please give your letter writers enough time to get back, and submit something. So don't ask them with like 2 or 3 days or something like that. Please give them enough time to write a good letter. All right. And 1 month notice is good. If you're applying now, you can let them know right away. Send them reminders when things are due and double check. It's nice if you can get it done a little bit before. Give them information about you. Don't assume that they know a lot of information about you. You can send them even, a kind of a draft or an outline of your experience. A lot of letter writers, if they're your science teacher or math teacher, they're not going to know what you do in your free time and your extracurricular programs and things like that. Hi, Max. We're talking about the application here. So if you missed some of this, you can ask some questions.
And we are
Um,
taping it so you can watch the recording later.
yeah. And it is the internship application is available now. I'll go back to that slide. And choose strategically and wisely who should write the letters, right? So, you probably want someone who knows you well and is a big supporter of you. You probably want someone who would know your skills in, coding or science or math and things like that. Um, Even someone who was a leader of like a STEM informal club, like an after school club or something like that. Those would be people that would be able to really talk about who you are and your skills. All right. Make sure you have time. Don't wait till the last minute. Read through things, submit before the deadline, edit, take another pass. Make sure if you know someone who is good at grammar. You can always have them look it over at the end. Um, if you know for sure that you're talking about your math skills, for example, get your math teacher to be the one to write up your recommendation or something like that. Look and see a lot of our mentors are come back for multiple years. So if there's a particular mentor you would really love to work with or a couple of mentors, note it and let us know. That's actually really helpful to us. And we've definitely matched people because they knew that there were mentors that they really wanted to work with. And then, we like to know who you are, not just related to your science skills, but, like things that you like to do in your free time and skills that you have that are just personal interests and hobbies and things like that. All right. So I'm going to just quickly go back so that Max can see. You can go to the N3 website and go to the internship page, and you can read about the internships and you can start the application there. All right. Okay. So now, before I move on, I do want to check, is there any question that anyone who's going to do an application, do any of you have any questions?
There's nothing in the chat.
Okay. All right. So, without further ado, I want to introduce. Can you see the text?
I saw the purple screen with the pretty picture, but I just see Brian's face now.
Yeah.
Now it's
Let me
fading
see.
away and turning into
Let me see if that
satellite.
I had an issue with that slide, and now I don't see the text of that slide. Let me see if I can find the actual text. Or Brian, you could just introduce yourself. And then you could start your slideshow.
Yeah, that's fine.
I don't know why I had it the picture was flipped upside down. I don't know. It was very strange.
Very strange happenings. Well, hi everybody. My name is Bryan Méndez. I'm an astronomer at University of California at Berkeley. I work across campus at the Space Sciences Laboratory in the astronomy department, and I partner sometimes with the Lawrence Hall of Science. Um, I do work in education, mostly for NASA, and have worked with the N3 team since, what was that, 2021, I think, when we started. And I've been as Wendy had mentioned, I've been as part of my work on the team has been developing curriculum for high school, as well as providing professional development for their teachers. And also, I mentored a student one summer, which was very fun. I enjoyed that a lot. So, that's about me. If you want to know more, you can ask. But I want to tell you about this cool mission that has recently launched and is getting ready to get started with science observations. So I am going to go forth and share, make sure I share the sound. Right. And let's launch this. I'll try again. There we go. You'll see my slides.
Yes, I see.
Excellent. Thank you. Okay, yeah. So the name of the mission, as you've heard a few times now, is called the Carruthers Geocorona Observatory. We do not shorten that or abbreviate it. We definitely never call it CGO. If we shorten it at all, we simply call it Carruthers. This is NASA's first mission to study Earth's exosphere and to be entirely dedicated to that study. So, what is the exosphere? Well, the Earth has all these layers. We live down here in the troposphere, airplanes fly up in the stratosphere, the top of the mesosphere is where we call space, thermosphere is above that, and then the highest level is the exosphere. And we actually don't know how thick it is. I'll mention that this graphic that you're looking at right now is very much not to scale. Earth's atmosphere is very thin compared to its radius. However, the exosphere may not be that case. Um, Currently, we know that it starts about the top of the thermosphere, which is about 300 miles up. Um, but we do not know how far it extends. We suspect it may extend like halfway to the moon. So lots of big unknowns. One of the reasons why we are having this mission. So the exosphere is gaseous and it's mostly hydrogen gas. And the density there is extremely low. The particles are so spread out that they almost never run into each other. So when you think about like the kind of gases in the air that you breathe, that air is relatively very dense. Those particles are bouncing into each other all the time and doing all kinds of normal physics that we know about with particles that interact a lot. Out in the exosphere, the density is so low that these particles almost never encounter each other. The hydrogen atoms can be seen by light from the sun that they scatter. So you have ultraviolet light from the sun. It comes in, it hits the hydrogen atoms, and then those hydrogen atoms kind of scatter that light in all different directions. And we call that glow that you can see in pictures the geocorona. And so that name is kind of in analogy to the corona that we see around the sun, right? That glow around the sun is coming from its extended atmosphere, and so the glow that we see around Earth in ultraviolet light is coming from its extended atmosphere as well. Now, before our mission, there had only ever been a total of 4 images of the exosphere ever taken. And most of these images were taken by spacecraft who that wasn't their prime mission, right? It was a target of opportunity. So, for example, I'll tell you all about the Apollo mission in a little bit, which was the first image. But like the Galileo spacecraft in 1992 was headed out to Jupiter, but in order to get up speed to get out to Jupiter, it was doing these flybys of Earth. And so on one of its flybys, it pointed its ultraviolet camera back at Earth and gave us this picture where we could see this extended glow of the exosphere. The Earth is this kind of whitish area in the center, and I believe that red dot's probably the moon. SOHO is a spacecraft that studies the sun, and they needed to get rid of certain wavelengths of ultraviolet noise in their data. And so they did a full sky look, and they actually looked back at Earth and managed to capture this image of Earth's exosphere, also in ultraviolet. And Procyon was the most recent mission. Again, it was using Earth as a flyby to pick up speed and just happened to catch a picture. So that's it. Those 4 images of the exosphere are all we've ever had until our mission. Now, let's first talk about parts of the Earth that aren't the gas. Let's talk about the magnetic field, right? So Earth has this magnetic field. It's kind of similar when you're close by the Earth. It's very similar to the magnetic field around a bar magnet, and it interacts with electrically charged particles. So there are those kinds of particles that share space with the mesosphere, the troposphere, or sorry, the thermosphere, and the exosphere. Those are charged particles that we call the ionosphere. So it's kind of sometimes confusing, right? Because the ionosphere shares the same locations as those other layers, but because the particles are charged, they actually behave differently because they respond to the Earth's magnetic field. And likewise, when the solar wind particles are coming toward Earth, they are also charged particles, mostly hydrogen protons, and they feel Earth's magnetic field and are deflected by it. So the Earth's magnetic field kind of acts like a shield that protects us from the incoming solar wind and creates this kind of magnetic bubble around the Earth, which we call the magnetosphere. The exosphere is larger than the magnetosphere, we believe, but again, we don't know exactly. And the other thing we don't know is, are there any interactions between the magnetic field and the exosphere? We don't expect much because, as I said, the particles out there are neutral, but there are some possibilities that I'll mention later. And by the way, if you have questions before I get to the end, feel free to drop them in the chat. I can see that right now. So if there's any questions, I can answer them in the moment, which I know is sometimes helpful. And why do we care about the interactions of solar wind with the magnetosphere? Well, if you were paying attention to the news last week, we had an enormous solar storm that impacted Earth's magnetic field and created what we call a geomagnetic storm. And these storms, they have all kinds of effects. Many of them are, kind of benign. We saw the aurora as far south as Florida. People took pictures of the aurora in Florida last week, as well as in New Mexico, which is pretty far south for the aurora to get to. And that's one of those more benign aspects of this kind of space weather, these geomagnetic storms. But the storms actually do affect, especially our technology, especially the technology in space. You get huge increases of charged particles in the ionosphere and beyond, and those can damage satellites that are out there. They produce radiation, which can be dangerous for astronauts who are out in space. And then they cause lower in the atmosphere all kinds of interesting electromagnetic issues, some of them requiring airplanes, for example, to not take polar routes. They have to take the longer trip around if they're going, say, from um, California to middle of Europe, right? Normally you'd take a fairly high latitude route, but if you have one of these solar storms going on, they're going to route you around. Takes a much longer time, uses a lot more fuel. And then we have disturbances in the ionosphere, which can interrupt radio communications, which can be trouble when you're using those radio communications for all kinds of things. Our GPS satellites are affected by this because they're communicating to, your phone to figure out where you're located. They're moving through, those signals are traveling through the ionosphere. And when the ionosphere gets really stirred up during these storms, then your GPS will start to lose a sense of where you are. And one interesting example of this that has been kind of rising to attention in the last years because it's had actually really large economic impact is modern agriculture, this big, commercial agriculture that uses huge tractors that are basically automated, right? There's not a person running them. They're robotic and they're guided by GPS. And what they've discovered is that during periods of high geomagnetic activity, the GPS can become so unreliable that the robots basically shut down. They're like, okay, I don't know where I am, so I can't continue driving. So they just shut down. And a lot of productivity is lost during those periods when the robots are shut down. And they have calculated the financial loss into the billions of dollars for the agricultural industry because of this effect. So, knowing about space weather and understanding how to predict it and figure out how we can maybe even, work out technological solutions to its effects is something that we're keenly interested in understanding. So the exosphere itself, because it's bigger than the magnetosphere, it's the first part of the Earth system that encounters the solar wind. And so there's possibly some interesting shape to the exosphere. It may not be spherical because it might be, experiencing kind of like a wind pressure that's pushing on it and perhaps creating a coma-like tail that we see like the magnetic field doing, but maybe not. We're not sure. One of the things that we really would like to investigate is an interesting process called charge exchange. And this is actually, it's technically a chemical process. This is where you have a charged particle, an ion, that meets up, has a close encounter with a neutral particle, and the electron from the neutral particle jumps over to the charged particle. And so it's kind of like the charge switches from, one object to the other. That's why it's called charge exchange. The interesting thing about that is when you have that kind of charge exchange going on, especially in the exosphere particles are pretty slow moving, but fast moving high energy particles from, say, the solar wind or from big strong currents that are running through the magnetosphere during a geomagnetic storm, those are going to be fast moving ions. And so when a fast moving ion exchanges charge with a slow moving neutral particle, then what the kind of output effect is that the current got slowed down and therefore reduced. And so we actually think that this may be a main way that Earth recovers from geomagnetic storms, right? So the solar wind blast comes in there, all that energy from the blast makes the magnetic field shake around, starts driving these strong currents. And then the only way, or the prime way we think for the energy to dissipate is through this charge exchange process, which is actually kind of giving up its energy to the neutral particles in the exosphere. So this is a process that we'll be able to study with the Carruthers Geocorona Observatory. One of the other things that is of interest to our science team is studying how planets lose water. So on this slide here on the left is a artist rendition of what we think Mars may have looked like 3 billion years ago, right? We think Mars was actually pretty Earth-like. It had very large oceans, probably had a thicker atmosphere, and therefore probably looked a lot like Earth. But of course, the picture on the right is what Mars looks like today, and that has been due to the loss of its atmosphere. There's many processes that are trying to be understood now about how Mars lost most of its atmosphere. But one of the possibilities is particles basically escaping through its exosphere, especially water. Water can be lost this way because water is made of two hydrogens and an oxygen. Well, there are one of the common ways that that molecule can break up is that when it's in the atmosphere, ultraviolet light from the sun will break it apart, right? Just breaks it up into its constituent atoms. And so the oxygen atoms, which are heavier, tend to sink, but the hydrogen atoms, which are so light, will just rise up, and they'll get into the exosphere. And if they have enough energy, some of them eventually leak away into space. And so it's kind of a slow leak into space, but for Mars, that slow leak happened quickly enough that Mars became kind of barren within the last 2.5 to 3 billion years. The same process is happening on Earth, much slower. Earth is a lot more dense and has much stronger surface gravity, so it holds on to its stuff better. But the process is happening, and Carruthers will be able to study that process. And one of the reasons that we want to use Earth as like this natural laboratory is because if we can understand how long a planet can hold on for its water, then it helps us kind of understand habitability for exoplanets. When all of these exoplanets that we're starting to discover around the galaxy, we find them at different sizes and different locations to compared to their star, different distances from their star. And when we try to model atmospheres, one of the things we want to be able to know is, yeah, how long could this planet hang on to that atmosphere before its density drops to the point where water would dissipate? Meaning the period of habitability on that planet is, a period of time. It's a fairly long period of time for the Earth, but it was a relatively short period of time for, say, Mars, and we'd like to understand how that works. All right, now the name of our mission is named after Dr. George Carruthers, who's the in this picture here on the right. He was a researcher at the Naval Research Laboratory in, I think that's one in Washington. And he invented a telescope, the first telescope that could take images of high energy ultraviolet light. And this picture here shows actually his first prototype of that telescope. The telescope was chosen to fly Apollo 16. Oh, is there a question?
Carruthers is the person on the right
Yes, he was the person on the right.
in your picture, right?
Yeah, and this is George Carruthers here in the center behind the telescope in this photo.
Maxwell, did
Um,
you have a question? I think you might be off.
oh,
You may not be muted. So if you don't have a question, you could mute yourself.
okay. Yeah, so as I was saying, the telescope was chosen to fly aboard the Apollo 16 mission and be set up on the moon so that it could take ultraviolet images of astronomical objects. Doing this from the moon is important because the Earth's atmosphere blocks all of this ultraviolet light from space. So you have to get your telescope above the atmosphere. And at this period of time, one of the ways to do that was to put it aboard one of the Apollo capsules. So this picture is actually during a training session that Dr. Carruthers was having with the astronauts. I'm blanking on his name. His first name is John, this astronaut, but I can't remember his last name. Young, I think it's Young. And he was the main astronaut who deployed the telescope. So Dr. Crothers was training him and the other astronaut who walked on the moon for that mission. And here's a picture from the mission itself. The telescope right there where the arrow points was deployed into the shadow of the LEM on purpose so that it could look around the sky and point at a bunch of different astronomical objects. And here's a John Young again, but if you notice, he's off the ground here because this picture was being taken while he did one of those cool jumps that you can high jumps that you can do on the moon, which you can't do on Earth. Now, when they brought the film canister back, which is here shown in Dr. Carruthers' hands, they, had a look at what did they see? What did they manage to get pictures of? And when they looked at the picture of Earth, they could see the glow of the exosphere around it, but they were surprised to see how big it was. In fact, they were surprised to see that it was bigger than the field of view of the camera, which means it's so big that the moon was too close to see it all, right? So that was a big eye opener. No one expected the exosphere of Earth to be so large. And that being one of the four images that I mentioned before, we haven't had a lot of understanding of just how large it can be since we haven't had very many observations that are farther away than the moon. So that's why we've built our telescope. Um, our observatory, I should say. It consists of two imagers, which are shown here. They have these are the doors that protected the imager um, apertures during launch and the early flight stages. The instrument was built at Space Sciences Laboratory at UC Berkeley, and it basically still uses the same technique that George Carruthers invented, which uses the um, effect of light hitting um, particles where or sorry, materials where the electrons are kind of loosely bound, knocks them free, and then channels them down into a pixel that will then hit a phosphor screen. The phosphor screen produces a visible light photon, which is then picked up by the detector. In Dr. Carruthers' camera, that was photographic film. And of course, in these modern detectors, they're solid state chips, very similar to like CMOS chips that you have in your cell phones. And here's the spacecraft bus that was built at BAA Systems in Boulder, Colorado. Fairly simple electronics to kind of run the power to the instrument, to store data, to transmit data, um, to run the reaction wheels, and also to use the thrusters when needed. And we get powered by a nice array of solar panels, which we're just going to point at the sun most of the time. And one of the things that I like to point out, this is the spacecraft almost fully completed, is, you've seen these people in these pictures, working on the spacecraft. And, in order to make a mission like this really come to reality, takes a huge number of people who have to come together, have to design, build, test, all of those things to get it ready for science operations. And it's hundreds, almost, maybe even sometimes as big as 1,000 people could be involved in a mission. And this is a relatively small mission, I should say. We only have one instrument. Here it is at Kennedy Space Center right before it was put aboard the rocket that took it to space. And, I was always kind of amazed when I saw these pictures for the first time of it all together. I was like, wow, it's kind of cute. In fact, it reminds me of a robot. In fact, a very specific robot. And I'm going to see if it strikes the same robot in your mind. So I'll ask you to use the chat. And on the count of three, I want you to type in the name of the robot that it reminds you of. Okay. So let's go. One, two, three. Okay. Lynn says R2D2. Anybody else? There you go. Yep. Sarah's got it. Wally. Yeah, that's the one that I saw. And then when I've done this presentation, in fact, when we were at Kennedy before
R2D2's the only robot name I can think of.
Yeah, when we were at Kennedy before the launch, I was giving presentations like this to a lot of different crowds, and I would ask everybody that same question, and almost universally, people thought that he looked like Wally, and I'm like, yeah, Wally was the one that struck me too. And I'm like, yeah, cute Carruthers spacecraft. All right, so we launched on September 24th of this year aboard a SpaceX. Darn, I forgot the type of rocket already. I had it ingrained in my memory. It's one of the bigger rockets because we had three satellites aboard it. Um, the main mission, in fact, was the IMAP mission because they were the big one. They had like a dozen instruments, and then we had two smaller spacecraft that were flying along for the ride. And we were all going to the same place, which is this gravitational balance point between the Earth and the sun. So we've got the sun in this picture, we've got the Earth. This is not drawn to scale at all, and it's marking out the five Lagrange points that exist as a result of both gravity and the orbital acceleration that Earth feels as it goes around the sun. And when you balance all those, or when you put those forces together, these lines here are contours of constant force, and there are five spots where the force is zero. And so it's like I say, a balance point. And the most stable ones are the closest ones, L1 and L2. We tend to like to stick spacecraft at these places because when you go there, you don't need to use a lot of fuel to keep yourself in that spot. Another great reason for going to L1 is because it's directly between the Earth and the sun. So if you're studying the sun, that's a great place to go and study the sun. And also, if you're going to study Earth, this is a nice spot too, because you can just turn around and point your camera at Earth and be looking at Earth the whole time, which is what we're doing. So here's an animation that shows our trip out to L1. So we launched on the 24th, and it took about 100 days for us to head out. That bubble there is the magnetosphere. Now we've put the size of the exosphere. You can see the moon going around the Earth, and there is the orbit, what it looks like as it goes around L1. So when it's sitting at L1, it isn't stationary, it's kind of orbiting that balance point. And like I said, it's such a nice balance point that it doesn't really require a lot of fuel to stay in that position. And the moon itself occasionally causes little pulls that can pull you out of orbit, so you need some fuel to push yourself right back in. But this, we hope, is far enough away to be able to see the entirety of the exosphere. The shaded cones here, the red and purple cones, show you the field of view of our two different cameras. So we have a camera that has what we call a near field, so it looks higher resolution, closer to the Earth, and then we have the wide field, which hopefully takes in all of the exosphere. And we do communications from way out there using NASA's Deep Space Network. Has these big dishes that communicate with a network of satellites. The data are from the network are sent to Berkeley's Space Sciences Laboratory. So they command the spacecraft and then receive the data from it. And then we send that data off to the University of Illinois, where our Peninsula investigator, whose name is Lara Waldrop, that's where she works. And she has a science team set up there who are running the data center for the mission and will be responsible for preparing data that will go out to the public starting in September. So about a year after launch, we'll have data products available for the public. Here's an animation that shows, shortly after launch, we open up the doors protecting the two apertures. So you can see the different sizes of the apertures. The smaller aperture is for the wide field, and the larger aperture is for the narrow field. And then these are our first light images. So, we opened up those doors pretty quickly after launch. We were cruising out toward L1, but while we were doing that, we were starting to take some images, seeing how the camera works, try to learn some things about it, how it behaves in space. And these were among the first images that were taken. So let me tell you what we got. On the left-hand side, we've got two images taken kind of at the same time from the near field instrument or imager. The top image is looking at the Earth and filtering out basically all the ultraviolet, or filtering out the specific ultraviolet that we think the exosphere glows in. And that wavelength has a special name in physics. It's called the Lyman alpha line because it's a very common transition, electronic transition in hydrogen. It's the ground state to the first excited state transition. Um, and that's what we think, because most of the exosphere is made of hydrogen, that's what we expect most of the geocorona to glow in. So we take images out of that, basically. We're looking at UV that excludes that so that we see the Earth all the way down to the highest levels of its atmosphere, or I should say of the thermosphere here. And we can even see some cloud patterns on planet Earth there. There's some background stars, and then there's the moon. This was taken actually near a new moon configuration. And then below is the Lyman alpha picture itself. And so this is the glow of the exosphere around the Earth. And then on the right-hand side, we've got the same pairing of filters just in the wide field. So we're seeing a much larger view. Here I drew in the orbital path of the moon, so you get a sense of how the moon moves through this field. And then down here we see the geocoronal glow. So we're really excited. We haven't done really any science yet on these images. This is all still in calibration phases. We just wanted to put these out there in the public so that they knew the instruments work, and we're real happy about that. One of the things that we should be able to do, because the mission's starting now, right at the time when the sun is just past maximum activity. So lots of solar flares, lots of sunspots, lots of geomagnetic storms occur during the maximum period. And then as we head on for the next few years, the sun will be quieting down and we'll have fewer and fewer of those types of events. And so that will allow Carruthers to see how does the Earth's exosphere respond to both these periods of heavy solar activity and periods of more quiet solar activity. We have enough fuel to last at least 10 years. So we're hopeful that after the 2-year mission is done, we get to continue looking at Earth for even longer. When we're officially done, we'll use the last bit of our fuel to push ourselves into a solar orbit. And so the spacecraft will just go around the sun for as long as it could be billions of years that it just hangs out there going around the sun, which is kind of fun to think about. Here's a video that I'll show. Hopefully you can hear it. Let me know if you can't. was trying to make sure I shared with appropriate things. This is just a quick video that we put together to hype up our arrival at the L1 point earlier this month. After launch, the Carruthers Geocorona Observatory began its journey away from Earth, separating cleanly, systems waking up and setting course for its destination. Cruising nearly 1,000,000 miles from home, Carruthers traveled to L1, a unique point between Earth and the Sun, where gravity and motion balance to give us a constant, uninterrupted view of the outermost layer of Earth's atmosphere, the exosphere. Along the way, the spacecraft checked in with the Deep Space Network, powering up its electronics and cameras and executing precision maneuvers, led by UC Berkeley's Space Sciences Laboratory. During the journey, the observatory began calibrations and other electronics testing, all to get ready for science. It began taking ultraviolet snapshots of Earth with these first light images on November 17, 2025. Wide field images revealing the full extent of the ultraviolet glow of the exosphere, the geocorona, and narrow field views uncovering fine details never seen before. And then arrival. Now injected into its operational orbit around Lagrange Point 1, the first NASA mission dedicated to studying Earth's exosphere will soon begin its science mission, observing, discovering, and expanding our understanding of the invisible boundaries surrounding our planet. Carruthers has arrived. After launch. There we go. All right. And so, as the video says, we are getting close to science operations. The plan is to begin in March. We have a NASA review next month that will, give us the go-ahead to start that phase of our mission. And if all goes according to plan, as I mentioned, we expect the first data products to be available publicly in September. So, I hope you'll keep your eyes to the space news and keep a watch on what we start learning about this fairly unexplored part of our own planet. All right.
Oh, thank you. So interesting, and you made it very understandable, Bryan, for a non-scientist like myself.
Good, good.
So thank you. Beautiful videos and stuff. All right. Does anyone have any questions for Bryan? Could be about anything about this mission and about just doing science communication.
Yeah, lay it on
Ask him
me.
about Star Wars collectibles too, I think.
If you'd like me to turn off my background, yeah, I could show you my collection.
Does anyone have any questions?
It was really great. I'm trying a different computer. Hopefully it works better. Thank you, Bryan.
Sure.
All right. Well, so I'm gonna if no one has questions, I know someone who does have questions, which is Josh. I'm gonna open up the I'm gonna share my screen for Josh because he will do the evaluation questions for all of you.
Thanks, Wendy. So, as you probably all remember, but maybe not, I'm with West End. We're the external evaluators for N3. And so our job is basically twofold. One, to collect feedback for continual improvement of the program, and secondly, to help document the impacts of the program on people such as yourself. So we just have a couple quick questions that we'd like you to fill out. If you can just fill it out in the chat, it really goes a long way to helping to provide feedback to the program and let them know how they're doing. So
Should we go to the first one?
yeah, let's just go to the first question.
All right. I was trying to put it in the chat, but can someone else put it in the chat? Because if I touch it, it goes to the next slide. So maybe someone could just put in the chat, question one, what takeaways are you leaving with this meeting with?
Great.
Oh, sorry. We got that. Thanks, Josh.
No worries. We'll just give everyone just a moment to type out a response. Um, Great. Thank you, Johnny.
All right. Do you want to go to the next question?
Yeah, we can go to the next question. Thanks, Maxwell. Great. And so the second question, what good things happened in the meeting today? Just another moment for everyone to put their responses in. Thanks for everyone that has responded. Really appreciate it. Okay, I think we can go on to the next one. And so what should we or the N3 program do differently next time? And if there's nothing you feel they should be nothing that should be done different, if you could just write NA or none or something like that, just we, have a response. Um, Great. Thanks, Maxwell. Thanks, Sarah.
Right, should we do the next?
Yeah, we can go on to the next one. I think there's two more. And so what happened? What did you want to happen but didn't happen today? Great, thanks, Sarah. And again, yeah, if there's nothing, then just write NA. That's great. Thanks, Sarah and Maxwell. Really appreciate the feedback. And I think we can go to the next question. I think there's one more. I forget.
Think that's it.
I think that's it.
Oh, that's it. All right, great. Awesome. Thank you all so much for taking the time to provide a little bit of feedback. Again, it goes a long way to helping the program know where it's at and what they can do to continue improving moving forward. Thank you.
All
Thanks,
right.
Josh. And for the people that came in a little late, this was recorded and the instructions for, good tips for applying for the internship. You can watch that part once we post the recording, probably, by next week, it'll be up on our website.
Yes, and I'm going to put the link for the um, information about the internship in the chat right there. So if anyone wants to look and see what the instructions are or to actually apply, you can get that information on that website. And we talked about next time meeting probably on
Yes, definitely
the
on
18th.
February 18th.
Yes. And
Yes.
hopefully we're going to have some interns talk about their projects.
We've already got 2 lined up, so I'm looking forward to it. I think it'll be really fun to have the interns talk about science, former interns, and about their lives since then and what they take away from N3.
Yeah.
All right, we'll see you all next month.
All right. Thank you, everyone.
Bye.
Thank you all.
Thanks,
Thank you,
Bryan.
Bryan. It was wonderful, as
Yeah,
usual.
really good.
Glad you liked it.
All right. Bye.
Bye.